and I'm KJ6 PST, a California transplant about 10 years ago, and so glad to be in Texas. Whoops. I think I have to watch out for... Yeah. Okay. The topic is... The acoustics are too good in this room. The topic is Balun Basics. It's a discussion, so I invite your questions at any time during the presentation. So if I make a stupid statement and you want to know what I'm talking about, by all means ask. The talk is in two parts. The first is a lot of definitions and explanation and description of what I'll focus on, which is the choke balun. And in part two, it focuses more on some hardware that I've put together. I'll have some handouts so you can look at it and touch it and feel it. And I also conducted a few experiments, so I'll give the test results as well. So for part one, briefly talk about my motivation, some early history of baluns, describe what a balun is, talk about balanced and unbalanced lines, some balun types and where they're used, and then introduce the question of is a coax a 2-wire or 3-wire, and then focus in on the coax-fed dipole issue in question. And then go through some definitions briefly. We'll discuss transmission line voltages and currents, and home in on the junction of coax with 2-wire line. And then look at some methods to reduce common mode currents, which we'll talk about, and introduce the Guanella transmission line transformer balun, and again focusing on the choke balun. And there'll be a summary, and I'll hold off on the references because I use the same references at the end of part two. Several years ago, I bought a Mosley mini dipole and looked up a Jerry Civic design to provide a choke balun for that antenna. And when I did that, I was curious about baluns in general, so that was the stimulus for trying to learn a little bit more. As you know, at Field Day, when we put up our towers and our Yankees, we insert choke baluns at the feed point for those. And so the question is, how do those work? In 1939, RCA, who was a pioneer in commercial television, placed TV antennas on top of the Empire State Building to cover the greater New York area. And these antennas were fed with coax, and they employed a sleeve balun for the coax feed to those antennas. And so, as far as I know, that was probably the first commercial use of baluns for transmission. So what is a balun? Well, a balun is a passive circuit that connects an unbalanced line to a balanced line with maximum power transfer. In general, a balun is a three-port device, but it can be configured as a 2-port. And as the picture shows there, it basically connects an unbalanced line to a balanced line. So one of the questions is, what do we mean by balanced and unbalanced? In order to introduce that, I know all of you are familiar with the ground symbol. What does the ground symbol mean? It's strictly a reference point against which we measure voltages. So it establishes a common point. And as shown in the diagram, whoops, sorry. Now I need my pointer. Oh, there is one here. There it is. Thank you. A very simple circuit, a voltage source, which is driving two resistors in series, and both ends of the circuit are connected to this ground plane, which we assume is an infinitely conducting plane. So there's no voltage difference between these 2 points, but current can flow across that. So a ground symbol is, again, a voltage reference point, and it's a path for currents to flow. And I mention this because later on in the presentation, you'll see those ground symbols, and this is what I mean by that. Okay, the question of balanced and unbalanced. To illustrate that, use, whoops. I'll get this right. Show a coax line where the center conductor and the shield are driven by a single voltage source. And the coax conductor is grounded, so obviously these 2 points are tied together. So that voltage then is impressed between the center conductor and the shield. A balanced is when two conductors relative to ground are driven by equal amplitude voltage sources that are 180 degrees out of phase. So this is a balanced system, this is an unbalanced system. Now there are two basic balun types. There are voltage baluns and current baluns. We are ultimately going to focus on the current balun, but in order to be fair to the voltage balun as well, we'll show where that is used. And the voltage balun is a magnetic flux coupled transformer, much like your power transformers, except a ferrite core is used instead of iron. Iron has a poor response at our frequencies. Ferrites have a much better response, so that's why they're used. The current balun is one which ensures that the currents passing through it are equal in amplitude and opposite in direction. These are called the transmission line differential currents. The voltage balun is designed such that if you center tap the secondary, then you get equal voltages in the output. So you can see this, the way this is configured, this is a 3-port device. You see the input port, which is unbalanced, and the balanced output port. The current balun also can be made into a 2-port by introducing a ground between those 2 points. So where are baluns used? I know all of you probably have digital transceivers, either in your trucks or cars or in your homes. And those transceivers have amplifiers, mixers, and ADCs, and a lot of them use baluns in that circuitry. The current balun, which is our focus, has application for antennas, for dipoles, Yagi-driven feed element, and any balanced antenna configurations. The balance of this talk will be primarily on current baluns. But in your transceiver, you may have push-pull amplifiers, either in your receiver or in your transmitter, that employs Balun circuitry. In your receivers, you may have double balance mixers, and those employ balance to feed the local oscillator, the RF signal, and extract the IF. And so those are very important components. And in addition, there may be a Balun feeding a analog to digital converter. And the reason for that is to provide some noise immunity signals going into the ADC. The coax, typically we think of coax as a two-wire conductor. Certainly it has the center conductor, which carries current, and the inner surface of the shield, which carries current. And those two carry the normal transmission propagation in coax. Those currents are equal in amplitude and opposite in direction. However, the shield is electrically very thick, and it can carry on its outer surface a third current, and this is where common mode current can flow. So the coax rather, can really be thought of as a three-wire line and not a two-wire line. And that's important as we look at the next slide. This is a diagram that probably every one of you have seen in your antenna handbooks. In fact, this is out of my 21st edition of the antenna handbook, and what it shows is the junction between a coax line and the arms of a dipole. And the problem is that when the shield current reaches this point where arm 2 is connected to the coax, it gives an opportunity for common mode current to flow on the outside of that coax. And that's something we don't want. And the reason why we don't want it is because if indeed there is common mode current flowing on the outside of the coax, the currents in each arm of the antenna are different. They're unbalanced. And as a result, in addition to the desired differential mode electric field radiating from the antenna, there's also a component of horizontal, which is due to the common mode current, and there's a vertical component, which is due to the coax shield current that's flowing on the outside. So those two then distort the ideal pattern of the dipole. So what we're looking for is a device, a Balun, that will equalize these currents and ensure that we have the ideal radiation pattern from our dipole and minimize the common mode current that would be flowing on the outside of that coax.
What do you use to measure it? What do you use to test it?
What you could do, in principle, in fact, there's a article by Llewellyn. It's an old article in QST, I think back in the 70s. And what he did, he took toroids and put a loop of wire and ran it to a detector. And the toroids were fairly small, and he would slip the toroid over the arms of the antenna to try to sense the amount of current that was in each side. And you could do a similar thing to the coax. You can, in principle, you got to get in a null zone here. You could also slip it over the coax and try to sense the coupling of that current, because it will induce a magnetic field in the toroid, and then your winding that goes to the detector would show that voltage.
Okay.
So it'd be a way of doing it. Oops. Better. I'm blocking you folks if I do that, don't I? Let's see if I can get over here. Okay, so now what I'd like to do is define balanced and unbalanced voltages and currents on transmission lines, two-wire and coax, look at differential and common modes on those. We'll also look at the magnetic fields, which is important. That's a key feature. And then we'll look at what happens at the junction between coax and two-wire lines. So again, this depicts a two-wire or bifilar line above a ground plane. One conductor is at plus V, the other conductor is at minus V, so this is a balanced configuration. The coax, the impressed voltage for this is between the center conductor and the outer conductor, which is grounded. So this is unbalanced to ground, this is balanced to ground. The currents on those two lines, again, the desired differential mode currents on the twin lead, equal amplitude but opposite direction, and a similar thing with the coax. The center conductor current is flowing, for example, to the right. The differential transmission line current on the inner surface of the conductor shield is flowing to the left. And again, the transmission line currents are equal in amplitude and flow in opposite directions. When a ground plane is present, ideally we know that the differential currents are inside the coax, and even though there is a ground plane present, they remain the transmission currents to carry power. When there is a ground plane present, there can be a finite impedance between the exterior of the outer conductor and ground, and that provides an opportunity for the common mode current to flow.
And you don't want the common mode current because it flows power back to your transceiver inside
It distorts the antenna performance, and that's what we're trying to avoid. This just shows the corresponding electric fields for those two modes. Again, the desired differential mode or transmission mode for the two-wire line, and the field lines for the common mode, where both conductors are at the same potential, and current for those is flowing in the same direction, which we'll see in the next slide. At first, it looks like these two lines are uncoupled, but it's not true. Because for the desired transmission line mode with current, let's say this one is flowing out of the board and this one's flowing into the board, we note that the magnetic fields for each oppose one another. And in fact, as you remove yourself further and further away from the twin lead, those magnetic fields drop to a very low value. That's what you want. That's why two-wire feed line works, because it's keeping the energy on those two lines that it's feeding your dipole. However, for the common mode condition, those magnetic fields add. They don't subtract. And so that is a very undesired condition. But as we'll see shortly, Guanella took advantage of that fact. Let's take a look at a junction between coax and twin lead. Let's assume for the moment that their impedances are the same. In that situation where there's no ground plane, so these are out in space someplace far away from any other kind of metal object, the coax currents are equal in amplitude, and the same is true for the twin lead currents. And in fact, since this conductor is connected to the center conductor of the coax, I3 has to be equal to I1. There's no other place for that current to go. This is a little trickier when there's a ground plane, and so we'll look at that. And here's the condition. When there is a finite impedance between the outer conductor of the coax and ground, that enables the current that reaches this point to say, oh, I've got two directions to go. What's the impedance if I go into the arm? What is the impedance if I go on the outside of the coax shield? So when that happens, then I4 is no longer equal to I3. And you can see that the difference that I common mode makes is the desired I2, this guy, minus the common mode current has resulted in a reduced current in this lower arm. So again, these two currents are unbalanced when we have common mode current flowing.
When that happens, doesn't that cause bias to the R's on your antenna? Is that what that I4 doesn't equal when you go to the I4?
It should affect it because the apparent impedance as seen is a little bit different. Yes. And again, just as we showed before, those common mode currents can generate electric fields, which is unwanted radiation. This you might feel in your shack if you have common mode current, you might get a little bit of a shock.
And Tom, since we're on Earth, we're not in space, we've always got a ground of some type, whether it's a connection
or Earth itself or other objects that are close by.
There's always a ground.
There's always something, right? So the current bound, again, where there's a line that's carrying both differential and common mode currents, when we insert this device, if it does what we want it to do, it ensures that only the desired differential balance currents appear at the output. So it's the operation or behavior of this device that we're going to focus on. And if it does what we say it will do, then what it means is that I3 and I4 are equal on the output side of that balun being fed by a coax at the input. If that's true, then from what we said before is I3 is equal to I1 because it's going to the center conductor, no place else to go. But inside the coax, we know that I1 is equal to I2. Well, if I2 is equal to I1, which is equal to I3, which is equal to I4, then the common mode current has to be close to zero. So we're going to focus on this guy. If it does the job that we ask it to do, then that will be the result, that'll be the desired result, that we equalize these currents. So how can we reduce common mode currents? And I'll focus on, or mention a few on the coax side of the junction, like the sleeve balun that we saw before, and then place much more emphasis on the one on the twin lead side. And you'll see where that will lead in a moment. So first we have the sleeve balun. How does that work? The sleeve balun is designed as a coax surrounding a coax. So here is the coax feed, it's feeding a dipole, and we insert this sleeve balun very close to this junction such that if it's a quarter wavelength long at our desired operating frequency, and it's short-circuited to the coax outer conductor at this point, then the impedance seen by any common mode voltage at this point is very high, and therefore that current is very, very small. So that's how a sleeve balun works. It is frequency dependent. And as I hope to show in a little bit, is quite frequency dependent, very narrow frequency range. And by the way, it's not very practical for HF because it would be quite big. It's a quarter wavelength. So for example, at 40 meters, a 10 meter balun would be impractical. Ferrite beads over coax. This is what Mark uses for our Yagi feed point baluns. And what it consists of, in that white tube that we see, that PVC tube, are a number of beads that are slipped over coax. And those beads are there such that when a common mode current would try to flow, it encounters a lot of inductive reactance. And so that impedes the flow of that current on the outside of the coax. And you recall that those white cylinders have a coax feed or coax connector at the bottom end where we connect our feed coax, and they have two pigtails at the top side. That connects to the driven element of our Yagis. Here's another way to implement a balun, and that's to wind coax around a ferrite toroid. And the reason why that works is, again, common mode current would attempt to flow on the exterior of the coax outer conductor, and it induces a field, magnetic field in the toroid, and due to the high permeability of the ferrite, that produces a large inductive reactance. That works, and you can see one implementation here. Depending upon the size of your coax, that'll affect a lot on how many turns can I actually get on that toroid. But that's one approach. Now, a little more history. A fellow by the name of Gustav Guanella in '44 published a paper in which he had the idea of taking a bifilar transmission line and winding it in a coil. And he did that because he was aware of the fact that there are transmission line differential currents that he would like to pass through, but there also could be some common mode currents. And in this depiction, the transformers are used to segregate the differential currents that flow through the transmission line from the common mode currents that are forced to flow through the large inductance. These transformers, again, are a conception just to show how you could separate out the differential currents from the common mode currents. I'll show you in a bit some transformer and an equivalent circuit that does not rely on that artifice. But again, the purpose is to suppress the common mode currents and to pass the differential currents. And this is the beginning of the transmission line transformer. And that will be the focus of the rest of the talk. Again, focusing on a choke balun, which is the most elemental form of this particular kind of transmission line transformer. And what Guanella took advantage of is what we talked about before, the fact that the differential mode currents create magnetic fields that oppose one another, whereas the common mode creates magnetic fields that add. And as a result, common mode currents, when there is a high permeability material within the coil, produces a very large reactance. So it opposes the flow of those common mode currents. In contrast, the differential mode currents produce a very weak field in that high permeability region, and the differential mode currents then pass through on the transmission line mode unopposed.
There's a number of loops, like if you do a coax balun with a number of loops, make it different impedance.
Yes, the more loops in general, the higher the reactance, right?
So some of the tribacks probably put 6 wounds, 6 inches in diameter, 6 loops, like a balun up there at the top. Tie what you tie to the antenna.
Are you talking about just an air where you're just taking, exactly. You can do that. In order to get a lot of reactance, though, you need a lot of loops. So this thing gets heavy because it's coax. And the more turns you're using, you're really affecting the bandwidth over which it can operate, because they then can become a resonant length and not provide the kind of choking action that you want.
Some of them were 6, I think some of them were 9.
Yeah, right. But this particular kind of balun, and this is the equivalent circuit for it, actually has a relatively large bandwidth. It can be several decades in bandwidth. So it can be used, if designed correctly, over the entire HF band, maybe up to 40, 50 megahertz. So this is the equivalent circuit for a bifilar toroid balun. What it shows is that the common mode currents are constrained to encounter this large reactance, whereas the differential mode currents flow directly through on the transmission line, and as a result, the output currents are the desired differential mode currents, equal in amplitude, opposite in direction. And this relates to the point you just made. The transmission line transformer has a bandpass characteristic that idealized looks something like this. This region is where the reactance is too small or the frequency is too low, and it's not providing much choking action. This is our desired operating region, and again, this can be several decades in bandwidth. And at some point, you reach what is known as the self-resonant frequency of the balun, and again, its performance begins to fall off. And this self-resonant frequency is proportional to the line length. So the longer the line, the lower the frequency. So you try to keep that line as short as possible. Now, I mentioned the sleeve balun and its reactance at a quarter wavelength is ideally extremely large. As a function of frequency, that inductance climbs and climbs and climbs. It's doing its job, it's choking off those common mode currents. But once you exceed that frequency, now that impedance becomes capacitive, and if you go too far, all of your choking action is lost. This is the lumped element equivalent circuit, where these capacitance and inductance would resonate to form a very large impedance. And I threw in some parasitic resistance because there's always some loss somewhere. So to summarize, the Balun use is not new, as all of you know. There are two types, voltage and current balance. The current balance are desirable because they equalize the currents in the arms of a balanced antenna. The current balun reduces common mode currents, and they can be implemented in several ways that we identified. The transmission line or Guanella choke balun can work over a very wide frequency range, but above the self-resonant frequency, the choking is no longer provided by that balun. So this is me, a beginner's look at balance, and what I'd like to do next. Are there any questions, by the way? I moved along rather quickly. Does anyone have any questions? Okay, well, I'd like to then go to part two. Like to,
Is that what it looks like?
yeah.
What's the foil for?
I'm sorry?
Is this a magnet? No. Or just?
That's a toroid. That's a ferrite toroid.
So is this the one that you said that the more coil, the better?
Well, we'll look at some of the design issues. So let's look at some Guanella. We'll look at some design considerations for the Guanella transmission line transformer. There will be a relationship that we want between the transmission line characteristic impedance and the load impedance. We'll look at choices of ferrite permeability and the number of turns, particularly when we're designing this thing. How many minimum turns do we need on this thing? And minimum turns is really the key. You don't want excessive amount of turns because that affects the self-resonant frequency. And above the self-resonant frequency, as we just stated a while ago, it's no longer inductive, and so it doesn't impede the common mode currents. So there are some design choices, and one of them is what characteristic impedance do we want for the transmission line, the winding that you see on those ferrite toroids that we just passed around? What reactance do we need for the choke? And how long should the transmission line be? We'd like to, again, keep it as short as possible so that we get the widest operating bandwidth that we can get. And you've seen this, so I'm going to pass through this. I'm going to again focus on a one-to-one choke balun. So in this case, the choice of Z sub C of the characteristic impedance of the line, if it's made equal to R sub L, the load resistance, then we have a matched transmission line. There's no reflection. That's what we want. We get most of the transmitter, most of the power from the source into the load. So that's one design choice. And I favor bifilar windings because, as Jerry Sivik showed in his publication, you can obtain a rather continuous range of characteristic impedances using the bifilar line, depending upon the diameter of the wire and the separation between the two wires. And you can use Teflon. I use Teflon tape to space those conductors apart, or you can use Teflon tubing, slip it over if you want higher impedance ranges. But you can see in this chart that the spacing between the wires results in an increase in characteristic impedance the further apart those two wires, which is what you'd expect. But you can do this now in a controlled way by putting that dielectric between those two wires and then using that glass tape that is being passed around to bind those together to make a rigid connection, physical connection. Okay, the choice of the inductor impedance. In order to keep the common mode currents small relative to the differential currents, a rule of thumb says make the inductive reactance 10 times the load resistance. So that would give you a rough idea of what the ratio of IC to I differential is. You want IC small, obviously you want all of your power in the differential or transmission line mode. And what I suggest is that when you choose the inductance, choose it at a frequency that is below your desired minimum operating frequency. That's to ensure that at your minimum operating frequency, that inductance is high enough to suppress those common mode currents. Now, toroids are not nice. They're actually very, very beneficial because they confine the magnetic field within the toroid. Very little magnetic field is outside of the toroid. And so there is an explicit expression that you can use to calculate how much inductance you need. And that inductance is such that if you say, well, I want the inductive reactance to be 10 times the load resistance, and that means 2 pi f, f is your operating frequency, times that inductance. So you can solve for that inductance. That tells you how much inductive reactance, how many ohms of inductive reactance do I need? And then you can use the expression that involves the ferrite that you choose, its permeability, and we'll look at a few numbers in a few moments. Mu zero is a standard quantity, and you can find it in any of physics books or electrical engineering books. That number is quite readily available. Pi is 3.1416. 2 pi r is the circumference of a circle, that nonsense. Anyway, with all of this, you then can solve for the number of turns that you need to wind on that. And so, again, on those toroids that got passed around.
Does that also provide the spacing of the turns?
Well, again, the spacing of the turns was determined by your load impedance. You wanted to match, again, for maximum power transfer, you want a transmission line that's matched to the load so there's no reflection. You don't want reflected power coming back. So again, Z sub C you choose just based upon R sub L.
Is
why you only wound on half the toroid on the example?
Again, it's a minimum number of turns, and you don't have to cover the entire circumference of the toroid, because those fields are retained within that toroid with its high permeability really captures the magnetic field. There's very little magnetic field on the exterior of that toroid. When the currents flow through those coils, that just stays within it. So there's a way of calculating how many turns you need. And on the toroids that I passed out, there was a little label, and it tells you what mix. It's a piece of scotch, right? That's mix 75. Mix 75 has a very high, well, I should back off a second. Some of the toroids, mix 31 and mix 75, are manganese zinc ferrites. They have very high permeability, but mix 75, for example, it begins to fall off at about 1 megahertz. So that's great for noise suppression if you're trying to keep noise out of your receiver from your antenna. You can wind a few loops around that. It's good for that. But it's not good to use as a transmission line transformer matching to your antenna, because its performance is falling off very quickly, even at high frequencies, 7 megahertz, 14, 20, for example. Mix 52 is not too bad. There's 10 megahertz. It's beginning to fall off. Mix 61, it maintains its permeability out to around 20 megahertz and then begins to fall off. And that fact that it's falling off is not a killer, as you'll see in a minute. And that's because even though, I trained my fingers, even though the permeability is falling off with frequency, the reactance is frequency times the permeability. And that product stays relatively constant even above where the permeability has begun to fall off. So it's still useful up to a point. So that's just a factor to keep in mind. Okay, and then the self-resonant frequency. When you wind the bifilar line around those toroids, you want to keep the number of turns to a minimum, because the overall length of that bifilar line is roughly n number of turns times the periphery of the toroid. So, and the periphery that I'm talking about is this side, and there are obviously two of those, and this thickness. So that's the periphery that we're talking about. So n times that is the length then of the bifilar line that's on here, and that is what determines the self-resonant frequency. Okay, now how did I wind those, and how did I make the bifilar line? Well, I built a wooden fixture, and I stretch the line between those two, and if I want to achieve a certain impedance, I take Teflon tape, which was in this container, and I wrap one of the conductors, because that helps to spread the second conductor from it, and that allows you to adjust the characteristic impedance of the bifilar line. And then with those clamped in place after I've done that, Then I applied the glass tape that you can see periodically along here to hold that together. And that's what I use then when I'm winding the toroid.
And they recommend using a shellac coated wire, is that correct? Or something on top of the coating on?
Great lead-in. The coating that you see on these wires is called heavy armored polythermales. And it's a bugger to try to scrape that stuff off the wire to expose the copper. They really do a good job when they apply that. But it's a high temperature coating, and it's an insulator, so even though the two wires touch one another, there's no conduction through that coating. And it, again, can withstand a lot of heat. But if you have a lot of heat in your Balun, that's bad. So you don't want to do that anyway. Okay, so for the wires that you see, the transmission lines on these ferrites, I was aiming for 50 ohms, and when I measured them in that fixture, when they were just stretched straight, it was about, that's a little high. It was, that curve got screwed up. They were about 57 ohms, not 67 ohms. That's a picture of them. And again, it identifies the kind of material that is used, their initial permittivity. This is a chart from Palomar Engineering, and they identify the useful ranges for certain applications, common mode suppression, tuned circuit, wideband transformers. Wideband transformers, what we're interested in when feeding our antennas.
Now, for what we use on ham radio, we want to use a 43 ferrite, right, instead of 31?
43 is better, 52 is better, 61 is better, right. Yeah, although 31, as I think it's Palomar Engineering, points out that you can use it as a choke Balun at quite a high frequency range for 31, so not bad. Okay, yeah, I guess that was close to right. When I wound those bifilar lines on the toroids and measured the characteristic impedance, I saw about a 7 ohm decrease. So my belief is that there is capacitance between the adjacent turns on the ferroid, and that helped to lower the impedance. So it's just something to keep in mind. It's not a killer, but it's just something to be aware of.
That's helping you, though, because you're headed down towards 50 ohms.
That's exactly a good point.
That's why you're winding them tight instead of using the entire
Right,
circumference.
right.
So you shorted the two ends of it and took your ohmmeter and checked the other end and get your 7 ohms?
I'm sorry?
You shorted one end of it together, shorted these two together, then checked out the difference in ohms between the center and the ground here? That's how you come up with your 7 ohm difference?
What I did, everything you say, I short and open. So I do two measurements, short circuit measurement, open circuit measurement, and then it's the square root of the product of that, yeah. So, so these are the characteristic impedance then of the toroid wound bifilar lines. And I was curious, what was the inductance? I had gotten recently an inductance meter, so I measured the inductance across all the mixes at various frequencies and compared them to the calculator. Remember, I gave you a formula that said how many windings do I need? And the agreement is, it's okay. It's not great, but for example, around 260 ohms measured, 205, not too great. This is a lot closer for mix 52. Mix 61, not too bad. And mix 75, not too bad, fairly close. Okay, I said that already. I measured. I took my rig expert analyzer and terminated those chokes with 50 ohms or close to 50 ohms and said, all right, what kind of VISWAR am I getting? And the SWR, not too bad, over the entire range from 1 to about 35 megahertz. It was less than 1.25. And I also looked at the impedance. Again, the real part of the impedance is fairly close to 50 ohms. It's about 52 or 3 here. The reactance is very low, as you'd expect and that you would want. And I used that information, by the way, shortly because, before I get to that, I used that information later because I was curious in what the efficiency was. How much power am I getting at the output compared to what I'm putting at the input? So I'll show that to you in a bit. I'm making this point about the choke voltages because remember we said that the output should be differential. Currents are flowing in opposite directions, equal and opposite, and the voltages should be 180 degrees out of phase if they're truly balanced. I inserted a ground, and I looked at the voltages relative to that ground. So that's what we're going to take a look at. And here they are. This is for the choke balun at 3 different frequencies. My signal generator only goes up to 20 megahertz, so I was stuck with that. But I used my scope, 2-channel scope, and looked at the voltages at either side of the load relative to ground. And indeed, you can see these are 180 degrees out of phase across frequency. And this was mix 31. I did look at a different mix, same thing.
You're not expecting that to change with the mix, right?
No, that should not change as long as it's operating as a balun, right?
And is that a measure of the mix or more the process that you use to build?
It's independent of the mix. This should be true if the balun is truly operating as a balun, then it should be correct, right? I was interested in efficiency, that is, how much loss is there in the balun. So I put a pair of the same mix, 52, back to back, so that I could put a load, and this is a calibration 50 ohm load that I put on one end to terminate it, and I used my analyzer to look on the input, and I used a signal source on the input, and I used a scope to measure the voltage across the input, and since I knew the impedance from those previous charts, I know how to calculate the input power, because I know the voltage, I know the input impedance. And I did the same thing over here, and here the load again is a very well-defined resistive 50 ohm termination. So I can calculate the back-to-back efficiency as P load over P in. And another method is to use the return loss. So I place a short circuit at the output and look at the return loss, two-way pass through a pair of them. And that resulted in a maximum of about 0.6 of a dB, which meant that the one-way insertion loss of just one of these is about 0.15 dB. No, not bad. It's okay. So now I compared the two measurements, the return loss measurement and the P out versus P in. And again, my signal generator can only go up to 20. So I overlaid the two, but there's fairly good agreement on the efficiency that measured with those two ferrite torites, choke balance. Now, Guanella used the basic design to create an impedance transformer. He was trying to take the output of a push-pull tube amplifier and feed a 60 ohm coax line with it. The impedance here is about 960 ohms. So he needed a 16-to-1 impedance transformer. So what he did, he took his basic building block and readjusted the characteristic impedance of each of these. And then on the high impedance side, he connected these in series, and on the low impedance side, he connected them in parallel. And that resulted in a 16-to-1 transformer. So I said, okay, why don't I try doing that? But I didn't want to change the characteristic impedance. So I used 50 ohm characteristic impedance devices, and I used a load of about 112 ohms, 2 carbon resistors in series, and then configured series parallel attachment on input and output, and measured the input impedance using my rig expert. And sure enough, the input impedance is about 28 ohms. So if you take 112 and divide by 4, you come up with about 28 ohms. And again, the phase relationship between those is as expected for differential operation, 180 degrees out of phase. So the Guanella balun has good operating bandwidth. It's relatively small size, I guess, if you call this small. It has good efficiency, and it can be configured using several of those in a series parallel wiring combination to achieve impedance transformation. And I said, okay, what about if the loads aren't balanced? What would happen then? So I grabbed a couple of carbon resistors for R1 and R2, and I started out with ones that are fairly close, so that ratio is 1-to-1. Then I chose this, which is about a 2-to-1, and then finally close to a 4-to-1. And I was just curious, is the phasing, the output voltages unchanged? So we'll take a look at that. And you can see the curves, the top curve is when it's 1-to-1. This is one side relative to ground. This is the other, and this, I guess that's magenta, is the sum of those two. And the reason why I displayed that on my scope is I wanted to see what happened as I changed those ratios of resistances. Did that stay the same? Because I want to make sure that the voltage across those two resistances, in fact, in spite of the fact that they're changing in ratio, still remain the same. Same current is flowing through that. And indeed, that's what this shows. It's maintained, and you can see one voltage is obviously decreasing in amplitude as I reduce that ratio. And in fact, this is a table for that. I did 2 mixes, mix 31 and mix 61, and the bottom line is that the voltages and amplitude track the change in resistance, which you expect if the same current is flowing through those two resistors. So, bottom line, in my opinion, guanella balance are preferred. They suppress the common mode currents. They maintain the differential transmission line relationship that we require to drive our balanced antennas. They have a good operating bandwidth. One can cover several HF bands. You can configure them as impedance transformers. They do maintain the transmission line currents and voltages, even when there's imbalance. And of course, as I said before, beyond the self-resonant frequency, the choking effectiveness just disappears. So that's my look at balance, in particular the choke balun. These are some of the references. I was showing Jerry Sivic's classic publication. Whoops. Oh well. I'm sure many of you may have this. I'll pass this around to look at. DX Engineering has a website that you can go to, and they discuss balance, they introduce balance, and then they give you advice as to what kind of balun is recommended for your particular type of antenna. So you might go to their website. Here's research paper on balance, and you asked the question, I believe, on how you might measure. Somebody did. Or Jerry did.
I actually pulled that one out and didn't get finished reading.
Yeah, it's in there. So I'll pass that around. This is Guanella's original publication. Jerry Sivic, in addition, or prior to publishing that booklet that's going around, had a rather thick volume with Noble publication. I Xeroxed the cover page and the index so that you can see what is contained. This I actually recommend before using that other publication going around. Has a lot more information in it. And then this is an article that I found online. And what it does, it assumes that the choke balun is working the way you want it to work. So it's choking off common mode currents. And with that assumption, then, he lays down some principles and applies them to various balun configurations as a way of analyzing those balun. So I recommend that as well. And that the one that I handed out last is this one. It is available online. Let's see. I think that'll probably do it. Okay, questions? I've bent your ear long enough. Yes?
For us lazy people, commercially available? Commercial sources?
You mean balance?
Yeah, no, of that particular type, yeah.
Yes.
Vanilla.
Oh, yes.
Always
Yeah,
been,
yeah.
Palomar is a good source?
Palomar is a source. DX Engineering is a source. If you want to make your own, the ferrites are available from Amadon, ferrites, and Palomar will sell you.
Palomar kind of more expensive, I bet, right?
How much are you saving building them yourself versus just buying it from Palomar? What's the? I mean, obviously it's interesting. No disrespect, but you know, can I build this in my shack for significantly less than I can buy it?
Yeah, I think the answer in general is yes, plus you have the satisfaction of knowing what you have and you measure it. I I really have to guess. I think that DX Engineering probably charges 100 plus for various balance that they provide. They're a good source, no doubt about it. If you want to build your own and you know what you have, you might want to use, for example, heavier wire than number 16. You might want to use number 14 because you have a need for it, or maybe not, or maybe use number 18.
That was like QRP mostly, so you could lighten up a little.
Yep. Any other questions? Well, then thank you. I appreciate it.
This is an open book test.
I'm sorry?
I guess that, what you're kind of talking about is my thought was, I'm gonna buy, 100 meters of magnet wire, I only need 5. Doing it as a class might make sense. Just
Well, you can
pushing
buy,
it out.
you can buy the magnet wire from Palomar per foot.
Oh, okay.
So I normally buy 60 feet just because,
You're gonna have extra
you're right.
spaces and-
But I found that number 16 is easy to work with. Number 14, even here, if you make a bifilar line and you try to feed it through, it gets me. What I do, I have a vise, and I clamp this in a vise with padding, and then I proceed to wind. And as you can see, there's zip ties, so the first line you zip tie it, hold it in place, and then you proceed to wind it. But even number 16 can give you a little bit.